Hello all, welcome back. Myself, I'm Sai Krishna from the Department of Aeronautical Engineering from the Institute of Aeronautical Engineering. Today we will be continuing our previous class regarding the solid rocket motors. Now, as we have discussed previously regarding the thrust stability and the vector stability, continuing the same, we will be studying about the integrity of the combustion chamber. Now, why the study of integrity is necessary, right? Initially, whenever what happens under your solid combustion chamber, the propellant, if this is my casing and this is my propellant or the unburned propellant surface, the exhaust gases tend to melt the upper surface of my propellant surface, which results in my erosive burning. And for the same, what I will be doing, I will be creating small sections, particularly the grooves or cog-like structures, to maintain my constant thrust profile. Now, continuing with the same, now as the mass flow rate or the mass flow rate of the gases or the rate of burning changes, there will be certain changes, because in a solid rocket motor, the entire solid motor itself acts as a combustion chamber, right? So as there will be a continuous form of burning inside a combustion chamber, we are supposed to understand the integrity till the extent or the extent till which it is viable to act as a combustion chamber. So the combustion chamber of a liquid fueled engine is rather small, and it's just big enough in diameter to allow the proper mixing of fuel as well as the oxidizer, and long enough to allow evaporation of the propellant droplets. The combustion chamber of a solid rocket motor is also the fuel store as well as it's large. In addition, since the high thrust is usually the main requirement, the throat diameter is also larger. The pressures experienced by each of them are about same in as modern rocket motors are around 50 bar. Designing a large vessel to accommodate high pressure and high temperature is much more difficult than the equivalent task of designing a smaller vessel. The skin has to take the pressure as the diameter increases and the thickness has to increase. Because of the large surface area, this has a major effect of the mass. In general, high tensile steels are used for creation of my solid rocket propellant motor, particularly the casing. Now, coming to my casing, as the casing will be in direct contact with the hot gases upon completely exhausting my solid propellant, we need some sort of thermal protection, right? Thermal protection to the walls to prevent the rupture of my combustor walls or my solid motor casing. Now, the walls of the vessels, which cannot be cooled by a propellant similar to my liquid fueled engine, and this imposes a considerable difficulty. As in case of liquid fueled combustion chambers, the temperature of combustion is much higher and than the softening point of the most metals, and the combustion products cannot be allowed to be in contact with the walls for any extended period, or disaster will result. The best solution is to bond the propellant to the walls and to cover the remaining inside surfaces with a refractory insulating layer. Now, this type of technique is called case bonding, because onto the case we are creating a small adhesive bond using a binder or something else to join or to directly extrude my propellant to my case. Now, what happened during this? As the propellant burns, it tends to maintain. Now, as the upper surface burns, the inner surface will maintain the required insulation over a period of time, right? Because initially the pressure would be higher. As the surface area decreases or increases, the pressure tends to remain same. So due to this, what happens? We will be having, and so this type of method technique of attaching the propellant to the case of the solid rocket motor is called case bonding, and it's used in most of the rocket solid motors. The grain which burns only on the inside surface, so the propellant itself acts as an insulator. Boosters are normally used only once, and so any residual damage that are caused to the walls when the propellant is exhausted is not much as important. A thin layer of propellant usually remains after burnout, means during the complete exhaustion of my propellant, and due to this sudden drop in pressure which extinguishes the combustion, where pressure particular care is required on manned missions, and for potential reusable casings a layer of insulating material is also placed between the grain and a casing before it's been bonded in, and any lack of active means of cooling for solid rocket components would make them unusable if the time factor were not important. The motor has only to operate for a shorter time, and after this time it doesn't matter if the components exceed their service temperature, although it is of course important that they are to be reused. So provided the fatal rise in temperature of casing or the throat of the nozzle that can be delayed till after burnout, then the motor is perfectly safe to use. This means for doing this on a well developed and used in early space program for atmospheric re-entry. The condition and the requirement are the same: to keep the most important parts cool for a limited time against the surface temperature higher than the melting point of metal. And this type of method is called ablative cooling. Right? When the surface is in fact a composite structure, the farthest removed the source of heat is the metallic structural component, which provides the strength as well as the stiffness if it is kept cool. This is covered with many layers of non-metallic material which have a dual purpose. First one, to cool off the temperature. Second one, to provide my strength as well as stiffness for the rocket motor. Now, this is a small figure which shows your thermal protection in the solid rocket motor. Right? A steel casing, right, which is being attached to my layers of ablative insulator, then to the material that is being burnt away or the propellant, and an insulating layer of cool gas. Now, as the figure tends or as the propellant tends to burn, they tend to burn from inside out, right? Now, the insulating layer of a cool gas can be exerted only while during the rocket is in operation, right? When in the initial stages, let's say start up or start down, at the time, the material that is being burning away will tend to provide the necessary amount of pressure that is required for the hot gas to maintain or necessary combustion to maintain. Whereas the layers of insulator made of composite materials will give you the necessary strength as well as stiffness, including the insulation properties towards the casing, such that the casing is well maintained well below its melting point of the material that is being made of. Now, undisturbed, they provide a good heat insulation, but when exposed to the full effects of the hot gases, they evaporate slowly or ablate. Right? This process extracts heat of vaporization from the gas layers nearest to the surface and forms an insulating cooler gas layer that is analogous to the provided by film cooling in a liquid rocket engine. The material that are used for combinations of silica fibers as well as phenolic resins and carbon fibers. The material is refractory, but because of its high fibrous and flexible, it does not crack and retains its strength and integrity even while being eaten away by the hot gases. A crack in an insulator would allow hot gases to penetrate the wall, right? And the development of these ablative insulators was a vital step in the development of both solid as well as re-entry capsules. The time factor was important. The process, which works only for a certain length of time, after which the heat reaches the structural material and the component fails. The time can be extended by including one or more heat sinks in the construction. These thick pieces of the metal with high thermal capacity are usually locally to slow down the rise of temperature of a sensitive component. They cannot be used for casings, but are often used in nozzle throats in which the sensitive structural components are smaller. The propellant is generally cast or extruded, as we have discussed earlier, into the required shape and is then inserted into the chamber and bonded to the wall. Right? The end phases of the charge, particularly the propellant, which should not burn the coated with the insulating inhibitor, and the other surface of the chamber are also insulated, and these activities are much easier if the motor is made in sections, and a large one may consist of several identical cylindrical sections as well as the top cap and the rear section containing the nozzle. The grain is cast in identical forms to match sections, and each form separately case bonded into the section. For very large boosters, the grain is cast directly into the casting section after the insulation is installed, and the sections are joined together to make a complete boosters. The technique is not used for third stages or orbital change boosters, in which the mass ratio advantage for quasi-spherical shape for the motor is paramount. Here, the grain is formed as a unit and bonded into the case. These types of motors often have carbon fiber reinforced plastic, also called as CFRP, which is also again called as a graphite reinforced plastic or GRP in United States walls, to improve the mass ratio. The joint between the sections, right? The joint between the sections have to be gas tight because they have to transmit the forces that are being arising from the high thrust of the booster, as well as the combustion pressure of 50 bar is sufficient to cause some deformation of the cylindrical section, and the joints must be proof against it. Now, what happens under your thermal protection? There are separate ways to manufacture my complete solid rocket booster. Complete solid rocket motor. Now, what happens with respect to first is either we create a charge or the propellant in terms of the grain shapes as we discussed in the previous class, then bond onto the case, right? This can be happened or can be made for different sections of a solid rocket motor if made by parts. If you want to create the same thing on a single instance or at a single large amount of solid rocket motor in a single instance, at that time what will be having? We will be providing charge onto the case directly. Now, during this, what happens? The charge has to be properly aligned. The case has to be properly aligned in order to maintain the necessary required pressure as well as the operating conditions. Now, coming to your intersection joints. For a larger booster, what we will be doing? We will be creating a small section. This is your first charge, this is your second charge. These will be connected using flanges. Right? Now, during this, what happens? These have to be airtight in nature such that the combustion gases that are in the solid rocket motor should not exit through these seams, as well as the outer atmospheric air should not enter inside the solid rocket motor through these cracks. So these are to be tightly bonded or made sure that nothing gets through. Now, the forces that are involved for testifying to by the large number of fasteners, obviously when looking at a booster, and each section is a cylinder with the wall as thin as possible of 12 mm to minimize the mass, and at the each end there are to be sturdy flanges to take the fasteners and to properly transmit the forces to the cylindrical wall. Turning the whole section from a solid material is a safe approach, but it's a costly, and the other methods of forming the flanges such as floor turning can be employed. There are two kinds of joints between the sections. One is my factory joint, and second one will be field joint. The factory joint is assembled before the charge is installed and results from the need to make up large booster casings from steel elements of manageable size. And these joints are protected by insulation. Therefore, before the grain is installed, are relatively safe. Whenever right, that is my casing. Now, if for example, let me just redraw it again on the two parts. Right. Now, let's consider this as two separate sections of my solid rocket motor. Now, and these will be my case 1, case 2. And these are supposed to be bonded together. Now, let us understand what is my factory joint. A factory joint is assembled before the charge is being installed. Means before loading of my propellant, I can join these two with the help of flanges, right, or the steel elements. This results in the need of makeup of large booster casings from steel elements for a manageable size. And these joints are protected by insulation before the grain is installed. So, before onto the casing, we are supposed to join two separate sections of a solid rocket motor together and put up a layer of insulation so that it will be ready to install charge right after it's left out of the factory. Now coming to a field joint, it is called because it's made in the field, that is at the launch site, and used because of the impossibility of transporting and handling a complete booster. Let's say the length of the complete unit after combining two separate boosters is 10 meter. So 10 meter, which is too large for us to transport. So what we will be doing, rather than joining them at the factory itself, we tend to join them right at the launch site, right? And at the launch site, using the same procedures that we are employed in the factory joint, we will be joining them one above the other to create a booster right during the launch. Field joints that allow the booster to be assembled and ready charge sections more or less at the launch pad. They have two safety issues. They are made under field conditions that are away from the factory and cannot be protected with insulation in the same way as a factory joint, because the two faces of a propellant charge come together on assembly and access the inner surface of the joint is impossible. The simplest pressure seal, that is an O-ring located in the groove in one flange and clamped by the surface of the mating flange. It is well tried and reliable seal, but requires very stiff and heavy flanges, otherwise the flexing of the thrust structure under thrust could open the seal. Organic seals like O-rings are generally not resistant to high temperature but should be protected. This is all more difficult because the junction of two sections in a large motor, such as a field joint, the grain is not continuous, so that it's not possible for hot gases to reach. It is possible for hot gases to reach intersection joint of the casing. And for a simple rocket fueled rocket, thrust acts axially. So the loads on the joints are even, the effect is close to joint even firmly. For strap-on boosters, there is a possibility of bending load caused by asymmetry of the structure. Simple phase joints are used to quite safely in solid fuel rocket, although the strap-on boosters a different joint is required. And to reduce the mass and to give some protection from flexing and as overlap joints are used between the sections. By overlapping joints, what happens? The pressure in the motor compresses these O-ring seals, while flexure can cause a small transverse movements in the joint faces. It is essential that the casing is a gas tight at operating pressure of 50 to 60 bar, as any leakage would allow hot gases to reach sensitive components. Being organic, O-rings cannot withstand even moderately high temperatures and should be kept within a reasonable range around room temperature. They cannot be exposed to hot combustion products, and a thermal barrier has to be placed between hot gases and the seal so that it does not form the seal itself and simply there to protect the O-ring. Typically, thermal barrier is flexible silicone sealant or thermal putty. Provided the seal is intact, then a small amount of gas leak past the thermal protection and equalizes the pressure. The small amount of gas cools but does not harm the pressure seal. While the thermal protection remains intact, the O-ring seals are safe, but it's either the sealant leaks or the O-ring leaks. Then the joint can fail. If the sealant leaks, what happens? Then the hot gases can reach the O-ring, which causes it to scorch or melt. So as soon as the melt, the seal fails. If the O-ring leaks, then the cooling gas that supports the sealant leaks away, and the sealant flows, which again may allow hot gases to reach again O-ring and melt it out away. This kind of failure has caused the loss of Challenger. What happened during this? An external temperature that is little above 0 degrees centigrade may have caused the O-ring in the aft field joint to become stiff and unable to follow the movements of the opposing flanges so as to remain leak tight. Hot gas leaked past the thermal putty and destroyed a part of an O-ring. Because as the O-ring is destroyed, the high temperature combustion products then escaped and damaged the main propellant tank, which contains the liquid hydrogen and liquid oxygen for SSME, which resulted in the loss of our space shuttle. Now, the joint that has been redesigned after the disaster, both to eliminate the thermal putty by replacing it with the J-seal and to use 3 O-rings in series. The J-seal is configured to seal more tightly when the internal pressure rises. It is interesting to contemplate that the rubber and silicon rubber, both of which are used domestically, can under right circumstances resist most of the undomestic temperatures as well as the pressures. Now, coming to our nozzle thermal protection, the nozzle as well as the throat are protected from the heat by the exhaust by using a similar technique to those that protect the casing. The problem is more severe because of the high velocity and of the exhaust gases. The main structure of the throat and nozzle is made of steel, but the layers of ablative insulator are applied inside. A heat sink can also be used in the throat to reduce the steel structure. The thrust is developed onto the walls to the nozzle, and the structure needs to remain within its service temperature until burnout. Let us understand this a bit further. In a solid rocket motor, the hot gases will be coming out towards the nozzle, towards the throat, then expanded through the nozzle. Now, what happened during this? The hot gases, if you are having any ablative material, right? The ablative material, they tend to erode, right? As the property of the ablative material, they tend to erode over a specified period of time, right? Over a specified period of time, because over a period of time, they tend to completely eradicate till the burnout, means there is no upcoming hot gases. Now, ablation, particularly heat diffusion, into the heat sink and thermally insulating properties of the throat lining keep the steel cool long enough to perform its function. And after burnout, it doesn't matter if the outer structure becomes too hot or too cold. It is worth mentioning that without a lining of the steel would reach its melting point in less than 1 second, but the lining prolongs its factor by 200%, means it increases the life of the nozzle, particularly the throat area, by 200%. Right? Now coming to your next is your nozzle area, particularly nozzle protection. We'll see small terms regarding my intersection joints. What happens during this? That is my case 1. This is my case 2. These are my flanges. Right? Now, what happens during this? When we are putting these two, particularly two cases together with propellant, we are supposed to make sure that there is no gas out, there is no gas leaking out of the hot gases flow. Some cases it being redesigned to let a small gas to pass to maintain the equivalent pressure with respect to the atmosphere. Right? Now, what happens during this? Right after this, if the same o-ring, which tends to maintain the pressure difference from the outside to inside and holds the seal, particularly the seal, long enough to maintain, to transmit the forces that are being exerted from the rocket motor as well as the heat from inside to out, which maintains the integrity of the seal in case if the seal breaks. Right? This is a similar example for a Challenger aircraft, that is a space shuttle mission with the code name Challenger. What happened is basically one of its solid rocket motors, particularly boosters, intended to fail. Right? They fail with respect to their seal, because previously before this incident, the people will be having only one seal to maintain that, one o-ring seal. So as the external temperature was little above 0 degrees and may have caused the o-ring to be stiff and unable to follow the movements, so the seal has been, it failed to remain leak tight. So what happens is the gas that is being created inside a solid rocket motor has passed the exit of the flange and is in direct contact with respect to my fuel tank, that is major fuel tank. As the hot gas are directly redirecting towards my fuel tank, what happens? They tend to boil up and the pressure inside the tank has increased exponentially. Now, this damages the propellant tank, which in turn losses the space shuttle. Now, after this issue, what they have done, basically, they have increased my single o-ring to 3 sets or 3 o-rings, as well as and changing my thermal putty with J seal. What happens to the J seal? Basically, the J seal is configured to seal more tightly when the internal pressure rises. because whenever the boosters are being made over a period of time, initially after the pressure gets rises, if you are going for progressive burn, the pressure as well as the amount of gases that are exiting tend to increase till the cross-sectional area as well as the pressure maintains. So as both they get decreased later on, they tend to give out a common form of velocity or common form of the pressure as well as exhaust gases. In other terms, thrust. Now, particularly in the next class, what we will be discussing is basically the ignition system for a rocket propellant motor, then few example cases regarding the solid rocket motor. These will cover your complete knowledge or vast knowledge regarding your solid rocket motors. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.